applause for Katie Malone.
Thank you so much for showing up. I know the last talk on the last day of the conference is kind of like not usually the best attended, so I really appreciate that there's such a great turnout, and I'm really excited to talk to you today. The topic of the talk is end-to-end data analysis in Python. So let me just very briefly introduce myself, because I feel like I owe that to you, at least if you're going to listen to me for a couple hours. So as he said, my name is Katie Malone. I am currently a data scientist at Civis Analytics, which is a software and services data science startup which is based in Chicago. And my role there is an R&D data science role. So I am in the enviable position of being paid to just sit and think about machine learning a lot. And I love it. And I'm very excited to sort of share a little bit of that with you today. Before that, earlier this year, I finished a PhD in physics down the road at Stanford. So it's kind of nice to be back in the Bay Area. Remembering how nice the weather is here, just in time to go back to Chicago, where it's not so nice. What I was doing in physics was I was searching for new particles at CERN at the LHC. So that's what my thesis topic was. We were looking for a new type of Higgs boson. We did not find a particular one that I was looking for, but I'm sure we're going to keep looking for stuff like it. Another project that I had before starting at Civis was I had the opportunity to work at Udacity and to teach a intro to machine learning course there, which was really fun and is one of the reasons I'm so excited to talk to you today, because I think machine learning is not just fun to do, but it's fun to talk about, and that's part of the reason I'm so excited to see such a big turnout today. Last is sort of a side project of mine is I have a podcast called Linear Digressions. Check it out if that sounds like it might be your jam. I find it very fun. So with that, let me get started. First by just sort of setting the scene for the afternoon so you know what to expect. So this workshop I am calling sort of the advanced beginner level, so hopefully everyone here has worked a little bit in Python before. Ideally also has a little bit of proficiency with pandas or sci-kit learn, and you kind of understand where those fit in the data science ecosystem. If that doesn't describe you, stick around anyway. You'll probably get a lot out of this. Also, if that's a little bit more advanced, you're a little more advanced than that, consider sticking around also, because every time you work through a problem, you kind of think about things you haven't thought about before, and that's what we'll be doing in this workshop, is kind of working through a problem together. And so the format will be sort of me talking, hopefully for not too long in a stretch, maybe 10 or 15 minutes, about things that are a little bit theoretically oriented. So talking about some of the kind of standard best practices in data science, ways to deal with the problems that kind of come up in the everyday practicing of data science. So what are we doing and sort of why are we doing it this way? And then I'll sort of toss it over to you to actually get your hands on the keyboard and code up an example problem that we'll be sort of working on together. So that's the point where I'll stop talking for a few minutes and allow you to work in the IPython notebook. I'll talk about that in just a second, but that's where you can actually try out the things that we've been talking about. So the problem that we'll be working on together is, I think, kind of a cool one. I don't know how many of you caught the talk this morning about Kaggle, but if you've done Kaggle before, or even if you haven't, it's a very awesome data science competition platform that's getting sort of it's a really great place to go and practice cool data science projects. There's another website we're taking this problem from. I call it sort of like Kaggle, but with a social good sort of orientation called Driven Data. And so that's where the project that we're doing today comes from. It's a problem of trying to predict which wells in Africa are going to have functionality problems. So we have a bunch of, it's a supervised classification problem. And so that's where the data should have come from. And hopefully most of you have had a chance to download it already, because I know that getting 100 people to download big data sets all at the same time is just asking for trouble. And so we'll be working on that sort of piecewise, iteratively, 5 to maybe 20 lines of code at a time. And in the format for doing the coding is I've put up a Git repo, which again, hopefully most of you have had a chance to clone already and get up and running. But these are IPython notebooks that you can run in your browser, and that actually is a really great way of sort of collaboratively coding. So that's where I would encourage you to do most of your work, and I have a little bit of explanation in there as well. In the same repository, you'll see sort of the African wells IPython notebook. There's also something called African Wells Solutions. And so this is for, obviously, the people who aren't here today and who might want to work on this asynchronously, but also if you find yourself getting a little bit stuck, that will be a good resource for you. Also, since we're getting started a little bit late and since we have such a big crowd, there might be a little bit of rushing sort of to get everything done at the end, and so you can use that as a resource. If you don't manage to make it all the way through to the end of the exercise, you can see sort of what I've done, use that as a model. And the last two suggestions that I'd like to make, first is that you pair up, you work in pairs or small groups, because you'll get a lot more out of coding this way, and I just think it's a lot more fun and it's a lot more dynamic. And also I've asked the people at the front, hopefully the sticky notes are sort of working their way towards the back. So I have sticky notes that I've been passing out. There's pink, green, and blue. And since this is sort of a big crowd, and I know that there's a big blend of experience levels and maybe how quickly you're getting some of this material working, I'm asking you to sort of use those sticky notes as flags to sort of, when we break up to do the coding exercises, to kind of signal how you're doing. So if you're working and everything's fine and you're not quite there yet, but you're good, maybe put up the green sticky note. If you get stuck on something, put up the pink sticky note, and then that will be a signal either to me or to the people around you, if they're done, that maybe you can use a little nudge. It's a way of asking for help without maybe feeling like you're imposing on anyone. And then if you get finished, I would encourage you to put up a blue sticky note, and then you can help the people around you, or I can just kind of survey the crowd. If I see a lot of blue sticky notes, I'll know to move on. So hopefully, most of you have sticky notes. If we run out and the people in the back don't have them, maybe move up closer to the front and pair with someone who does have the sticky notes, just so we can kind of stay synchronized that way. So with that, I'll actually stop talking for a moment and allow you all to sort of match up and allow the stickies to kind of propagate throughout the crowd. I'll also give you a minute or two for those of you who haven't had a chance to download the repository yet or to get the data set. This is your chance to try. Good luck. And last is that I made a few assumptions that are just sort of based on my laptop sort of local environment when I was putting this together about the tools that I had. So things like having sci-kit learn available, having pandas there. So hopefully you have all of that as well, because that's going to be sort of optimal for having you be able to complete this. So with that, I will stop talking for a moment and allow you all to pair up and make sure that you have either you or someone in your group has a working setup. And then when that is the case, maybe stick up, I said the green flag here, I guess maybe the blue makes a little more sense given our code. And then as soon as I see that all of you are ready, we'll move on.
Can you, where do you get these files there?
Yeah, so you don't have to download them.
I did.
Yeah.
Well, no, I
I'm going to ask you to link them.
but that's okay.
Obviously, you just stick them on like your screen, like that.
Katie, it's just like the last one that they have to sign up to be there.
Yeah, the plan is project and then sci-kit learn to sort of allow you to package together several different things into like a single peer usage.
Okay, so quick show of hands. Are most people there or getting there with the data? Are we ready to keep going? Mostly? Maybe show of hands people who want another minute or two? Okay, another minute or two. So just for those of you who are still working, if there's anyone who was having trouble getting the data, so what you need to do is you go to drivendata.org. There's a link in the IPython notebook that'll take you right to the correct page. But then along the right-hand side of that page, there's a button that says compete. You have to sign up for an account. So click compete, you click OK for all their sort of like rules for the competition, and then you'll be able to download the data. So if anyone was having trouble with that, this is how you do it.
All right.
Yes. Okay, so I think hopefully most of you have it set up. If not, maybe just keep letting it download. You'll have to rename the files, and I think there might even be a typo in what I call them in the notebook, so I apologize for that. But hopefully it's fairly clear how you can get them to have the same name. But what I want to do is go ahead and just get started. My goal for the first part of this talk, so this talk is going to be in 3 parts. So the first one is we're just going to sprint as fast as we can towards like having a working analysis that like has a result. And the goal here is to get as to the finish line as quickly as possible, kind of leaving some dead bodies along the way, and then we'll kind of circle back and clean up the stuff that we've done and do it in a both a more like correct way and in a like tighter and more like lovely code way, a lovely way in terms of the code that we're using. But this is going to be just the first pass, and then that way we have a benchmark that we can use for the rest of the time and sort of compare against as we're iterating on the analysis. So a few things we'll talk about this a little bit, getting the data in and getting it ready to use in a machine learning algorithm, and this is not as trivial as it sounds. We'll then decide how to actually build the model that we're doing, and then set up a very quick and dirty cross-validation evaluation framework. So with that, let me speak just generally about how you usually get started with one of these. You go from sort of a raw data set to a working model. So the first thing, which I've sort of set up for you in the IPython notebooks, is just reading in the data. And usually pandas is the best thing that you can use for this. It's quick and it almost always works. The next thing, which we won't be doing in this workshop, but which I do want to pause and just emphasize, is cleaning the data, because I think everyone who's worked with real data knows that it's usually not very well cleaned and well formatted. Working with data sets from someplace like Driven Data or someplace like Kaggle that takes care of this somewhat for you, but you always, usually when you start with a machine learning problem, you'll have to spend some time cleaning. That having been said, we're going to kind of skip over that today, but that would be an entire workshop all on its own. The things that we'll be working on are the things that are kind of in green today. Hopefully you can see those. but getting the data into a machine learning friendly format, building a simple cross-validation framework and a model, testing and evaluating the model, and then just iterating on those steps that are in green. So the first thing that I'm going to have you work on is getting the labels ready. So what you should have is 2 different files, one of which has all the features. We'll get to those in a second. The other one has all the labels. And so what we're doing, just to remind you, is we're studying the functionality of wells in Africa. And the way that the labels are actually recorded in the CSV file is you'll have an ID and then a string that says functional, functional needs repair, or non-functional. And the thing about machine learning is that it's usually not based on doing string comparisons, it's based on doing numerical comparisons, putting everything into a matrix and then doing various linear algebra things or what have you on the matrix. So putting something like a bunch of strings into it is going to break machine learning. So the first thing that you need to do is sort of make a mapping that takes you from these string labels onto a set of integer labels. And what I'm going to suggest that you do is that non-functional be mapped to 0, functional needs repair gets mapped to 1, and fully functional gets mapped to 2. And so there are a few different ways that you can do this. I'm going to have you stop talking in a moment and let you actually work on this. But since we're working on pandas, you can use something like apply or apply map. And there's also replace functions. So however you choose to do that, whichever seems to be the most intuitive way of sort of solving this mapping problem for you, go ahead and do that. But that is what we'll do first, so we'll let you do that now. Okay, hands on the keyboard. This is yeah.
Oh wait, well data
Yes.
Functional and non-functional, she suggests calling them 0 and 1.
Yeah. So yeah, just mapping those strings to elements. Key down there.
Transferring labels. Let's see.
That's one way to do it, like a cover. I'm still reading it. I think we're not using the test set of this for non-functional.
So they're only
Looks like there's a functional label, a non-functional label, and a functional needs repair.
So let's see, label map. Oh, okay, your code goes here. She wants to see this. Okay.
Bam.
Okay. So what's this gonna do then? So
Yeah, so now we have to change the status from
apply the
zero to one.
okay.
So
So labels, apply map, label map, and we'll give it labels. Yeah. So then we'll take functional and non-functional. Start by
don't know. We happen to have a version 3 lying around. Ironically, I don't think I have 3. Yeah, I think I have it in the last one, but I didn't. Yeah, maybe that was word with a friendly neighbor or something. Yeah. Right, so I renamed them.
Emotional space needs repair.
Yeah, what I would do is I would take this, the one ending in 0, rename it to will.
Yeah, and then what do you think?
If it's for the planet.
I don't know what you're trying to say.
You can look at the help for finance.
Oh, I already said labels. Oh, we already lost it. I think I should write it now. Okay. Huh, that's weird. It's already like printing. Oh, I see. It's that, and then here.
These ones are.
So it's printing 2.
Well, it's printing it out. It's like. Okay.
Yeah, but it looks like it's printing 10 things, and I only say print Y. It's 5. I would figure only print 5 of them. It's funny.
Okay, so you're dipping.
Yeah. Let me try. Let me just figure out what's really going on here. None.
Oh, this is not just the label. Sorry.
Is that ready?
Oh, right, yeah, okay, yeah, here, let me,
Friendly reminder of blue stickies if you're good to go, because that's not telling you where we are. I just want to make sure I'm moving very speed. So mostly blues? Okay. Maybe like quick show of like hands, quick show of greens, who's still working on.
There's 10 of these, even though it's DFS. Right? I don't know why.
Okay, maybe like one more minute and then we'll keep going. And then remember, if you're struggling with this a little bit, the solutions are there. So maybe feel free to like kind of hop in, go back to the
Yeah, I'm not sure if the downstream.
Yeah, it is. What's that?
Google like string comparison.
Yeah.
Okay, so I'm going to keep going. Reminder, if you're still like maybe a little bit getting caught up, feel free to like make use of the solutions to help you keep going. Also make use of your neighbors. They're very friendly. Okay, so hopefully what you have now is you have a set of labels that are ready to go in terms of a machine learning algorithm. And hopefully that wasn't too painful. Maybe you got a little bit acquainted with some of the magic of pandas. The features have the same sort of feature, problem, if you want to say, in that a lot of the data in the features is also encoded as strings. And so what I'm showing you here is in the orange box is what we were dealing with the labels. So there's like one string that you have to deal with for each row. The features, this is 4 rows of data from the features. So you can see that there's lots of features in these CSV files. And if you're sitting close to the front, you can also see that there's a lot of strings in there. So we have the same problem with the features that we had before with the labels. But doing something like, okay, I'm going to manually sort of sit here, think about how I want to map a given value onto an integer, that's not something that you totally want to do for 40 different features that have who knows how many different values for each of them. So I'm going to ask you to do the same thing. We're just going to repeat the exercise and convert it into integers. But doing something like a search and replace is not totally the way that you want to do this now. What you want to have is a function that you can pass in, for example, I have this. So you pass in the data frame and you tell it maybe which column you want it to transform. And then you want that function to automatically be able to figure out how many unique values are in that column and then just convert each one of them into a different integer. And sort of what's implicit in this is that we're not trying to make any statements about ordering the features. So before we said that functional is 2, functional needs repair is 1, non-functional is 0, and so that sort of implies an ordering to the values of the labels. We'll talk a lot more about this in a little bit. But we're going to kind of relinquish that sort of control that we have for the features. We're just going to say, like, just assign it to an integer. I don't care what the value of the integer is. Just make sure that they're sort of like mapped on. And so as sort of an example, these are a few lines of features that I've kind of grabbed out of the features table. You can see there's a bunch of strings that are encoding sort of like the source types for the wells, and that those are going to be, after the transformation, mapped onto just numbers. And this is just an example. You might have different values for, or a slightly different mapping. The other thing that I want to mention is you want to have this so that you can call it maybe just on one column at a time, because not every single column in the data frame is going to need to be transformed. Some of them are things like latitude and longitude, which are already numbers. And so I'm going to suggest that these are the features that you want to do this transformation to. These are sort of the columns that have strings in them. And then maybe just take this big list. I think this is even in maybe the notebook that I gave you, and certainly in the solutions. And just use this list of features and kind of like iterate through it, transforming each one as you go, if that makes sense. The last thing I'll add before I let you work on that is that one of the fields is a date. It's the date that the well in question was inspected. And time series data can be kind of its own beast. So what I'm going to suggest is that you actually just drop that column entirely, and we're going to kind of ignore it for the rest of the day. So with that, is everyone clear on sort of the agenda for the next few minutes? Does that make sense? Okay, so now I will let you hack away on the features. Good luck.
Did you hear what she said? I'm sorry, I was still trying to do the last part. What did you say?
Okay.
What are we trying to do now?
So it's the same thing that you did in the last part, but we're doing now, instead of doing the labels, doing the features. So you have a bunch of features that are encoding, that are saying things like, is it like a river, or is it a spring, or, and so those are all strings that need to be encoded as integers. So it's the same thing, but just a little bit more general.
With the transform feature column name.
So I would suggest that, so transform feature, that's right. So the goal would be to have, that you can go through like sort of column by column and say, for a given column, do I want to transform this one or not? And that these columns are the ones that you're going to want to transform. It's not, you don't want to, what I don't want you to do is try to transform every single column in the data frame, because some of them are numbers already.
So whatever is string
Yeah, so all the ones that are strings, basically, all of the types.
Transform is that into something?
I think
We should just copy that.
you can copy it over. Yeah, you can copy it over from solutions. I was gonna invite people to sort of like inspect and try to make up the list on their own, but I think in the interest of time, I'll just tell you to kind of grab it. Those are just all the types of all the columns that are string types, though.
Okay.
Does that make sense?
If you look at the data type, it'll tell you which ones are
So
strings and
two
stuff.
transforms. Okay.
Right, yeah. We're gonna do that. We're gonna do downstream.
So it's thinking right now, it's still processing.
Yeah, something like that.
Basically, it's translation. And this is just the picture showing there. And this loops over each of these values and applies this function here to each column.
You don't even need an one. I mean, zero. Oh, if you want to average.
Seems to be taking way longer than it should. Probably hit an error. Yeah, that's what it is. Stop this entirely at this point. The web browser just crashed. It's not even the IPython.
Do it for one, then these are
Can you get to the other types and things?
No, yeah, Firefox just totally crashed right now. Say something happened.
right, yeah. That is not text.
Did you kill it in the signal?
Okay. Alright. So copy this code for now, just keep moving.
Yeah, so what it should return is data frame that you send here, but now that data frame, the column is specified is transformed. So the idea is to be able to kind of like swap down the strings and swap in integers. So you can yeah. For a given column, so just kind of treat each column as independent. And feel free to like change these.
I thought this is what we put last time, so I don't know what happened, but it
Just
crashed.
don't have assets.
Yeah, it was just didn't have else if and else. I'm not sure why that mattered.
Yeah.
But, I guess if you need to, you have to do, no, you don't have to do an else after it. So I don't know why it worked. But anyway. So.
I'll do the same thing to all the other ones.
Well, we need to do this. Might be easier to like set up a dictionary or something.
So I can just loop through this.
Well, I need to get that list to work first of all.
She said it's
the very bottom or in the systems? Maybe. I mean, surely it's in the systems somewhere. Whoa.
You also might be able to get it if it's a string or not.
Yeah, here it is. So she typed it in the solutions. Yeah, I mean, I can probably look at it and see what all the different values are. Where are we? Transform. Let's see. So define transform feature. Return df column name. Okay, so this just returns a df when you actually insert column name. So first, let's take a look at. So did we make a df yet?
Yeah.
df. Labels df. So there's a labels df. Right. Features df.
So yeah, down here it's funny.
Df. What's that? So these are all the different names we can choose from. She just wants us to get rid of some of them though. But it looks like most of them.
Yes, it's.
Okay, so most of them are here. I think. Oh wait. Oh, that's right. So.
If you do features,
Columns.
Yes, okay. I'm close to catching up with you. I got it. Yes. Are you ready? Got it? Yeah. Perfect. Now we have Malone.
There we are.
We're a winner.
Right. So let's go ahead and call these.
Okay, we got it.
So, oh no, so prestige here is what.
Yeah, it still works.
So, this is just right. The apply map will be silent.
Okay, so then which one of these do we want? Let's go back here.
Yes,
So,
why
let's have to get rid of some of them. Which one is
why
why?
is it?
yeah, the date recorded, I think.
And so, apply, yeah.
So these are the
apply
ones she
map
says to keep?
To transform. If you,
Transform into, oh, you want to transform them into integers?
yeah. And it looks like you suggested dropping date recorded column.
Drop it, so wait.
Yeah, so, and the thing about this.
So I don't think you'll have to, transform launches just latitude.
Yeah, basically, presumably anything that's string. Now we'll need to do a general way to transform them into integers, though, if we're going to do that, right? Because
I think she had
transform
so loops through those three.
founder installer. Let's see, for column names. Let's see.
This is where the code is.
Column names. That's weird. These columns transform founder, installer, and WT name. Right, okay, so it only transforms those. I'm not sure why she was some of those transformed. Okay, so name columns transform those. Features df equals transform feature. So the features df is columns. Okay, so it just calls features df for each one. And so then this would probably want to make a set and find the otherwise find the unique features and then iterate them and number for like whatever number. So we could use like an ordered set or an ordered.
Sure, and you can have like, I think there's a lot of ways temporary
well, we could just take a list and zip it and enumerate it. We could enumerate a list of all of the features and then turn that enumerated list into a dictionary and then run through like that. Although we're probably out of time now. But I think I see how we can do it. Right, so let's see. So this should be the features transform. Okay, so we could add to this.
So I know this is definitely a tricky problem. Let me just quick show of hands. How many of you are done? Oh, okay, fair number. And then how many are still working? Probably slightly more. Okay, let me give it a couple more minutes, and then in the interest of time, we'll kind of keep going. But those of you who are still working on this, don't feel bad. This took me an embarrassingly long amount of time for how simple it is, and I hope you understand maybe now why it's worth spending a little bit of time and struggle in a workshop going through it. But that having been said, I'll give you a couple more minutes, and then we'll keep going.
So let's see. All right, first of all, yeah. So so it gives us a logical set. So the main thing that does is it gives us the unique values. So there were like 50,000 entries, but there's only 1,800 unique values. So then we can take that set. So call it unique values equals that set, and then we'll say we've got a unique dictionary equals predict with enumerate values. Let's see if that does one. Yes, we have one. So now we've got a number for each thing. Alright. So now what we want to do is yeah, so then we want to say so that would be let's see. So what do we want to do for that exactly? So in here we're going to end up with the data frame. So we're going to return the data frame. So we're going to say that but we don't want to do, but we have 180,000, so we can't just spell it out.
That was if just use the dictionary to look at the value and return the value.
Yeah. Yeah. So we want to do feature data frame, features data frame,
Funder will just give you value.
Okay, so let's keep going.
It's also going to be an index, maybe that's okay.
That was not super easy, right? Like, it's conceptually an extremely easy thing to do, like, oh, just string swap them in for numbers. But I think you've now like appreciated that sometimes this can be a little bit tricky. Hopefully, the code that you've been able to write here, this is something that comes up a lot, honestly, is with CSV files like this, doing the transformation of the strings into the numbers and the integers. So hopefully, if you've gotten this working or if you're using the solutions for a reference, this is a problem that now that you've struggled through it, may this be the only time that you struggle through it, and then you have this as a reference. So thank you for your patience, but again, sort of it's the first time you see these things, they can be a little bit tricky. Okay, so with that having been said, honestly, that was one of the harder parts of this, I think. So now we're going to start to get into the machine learning portion of this, and this I think is actually sci-kit learn makes this really easy. So let's talk a little bit about the way that we're going to approach this as a machine learning problem for a moment. And there's kind of two tacks that you can take in general with supervised learning. One is that you can do a classification, and one is that you can do a regression. So classification, hopefully you've at least heard that before. And the idea is that with classification, you have sort of like discrete categories of things, and the problem is just assign each instance to a category. And kind of encoded in that is that there's no ordering to the categories. So an example of a classification problem would be, is this chocolate, strawberry, or vanilla? And there's no natural ordering to those three things. They're just three things that are different. Colors would be another example. And so another way of saying this is that it's a non-ordinal case. So there's no, like I said, no natural ordering. Regression has a continuous output, sort of by default. And so an example of something you might get would be if you're trying to write a machine learning algorithm that can predict the ages of everyone in this room or the incomes of everyone in America. Those are numbers that will sort of span a very large range, and they have sort of an ordering to them, and that would be a sort of classic regression regime. And I think that thinking about this problem for a little while as a data scientist, there are a couple different arguments you can make. One is that you can say this is a regression problem because on one extreme we have functional wells, on the other extreme we have non-functional wells, and in between there's this sort of intermediate point, which is functional needs repair. And that's sort of what we've implicitly sort of said by assigning 0, 1, and 2 in the first stage when we sort of did the encoding of our of the well functionality. However, one of the things that can be tricky about approaching this sort of discrete output and trying to use a regression to get the answer here is that regression is going to give you this this thing where the number that it's going to give you a floating point number, right? It's not going to give you 0, 1, or 2. It might give you something like 1.75, and then it's kind of up to you to figure out what that's supposed to mean. Does that mean that it's functional? Does that mean it's functional needs repair? Like, I don't know. Who's to say that functional needs repair is even like halfway in between non-functional and functional? So this is actually like it's a more challenging problem than it might seem at first blush. And so I think that you could make a strong argument either way for classification and regression. What I've chosen to do for the rest of this is to treat it as a classification problem, because then you don't have to worry about this post-processing step. But one thing I'll argue for later is that sci-kit makes it so easy to try both regression and classification techniques that for something like this, when you're in doubt, it's worth kind of just trying both of them and seeing which one works better. That having been said, I'm just going to treat it as classification, but I did want to acknowledge that that's actually a more complicated thing than it might seem. So this is an example of just what is this actually called, because we have categories, but they have an order to them. This is an example of ordinal modeling. So this is ordered categorical output. And this is not something that's like sort of supported kind of out of the box in scikit-learn. Scikit-learn is what we'll be doing all the machine learning with. So again, you have to either treat it as a classification problem or as a regression with bucketing. And I would advocate in production time just sort of doing both and going with whichever one seems to be giving you the best outcome. So that having been said, because we're trying to just get to an answer as quickly as possible, I'm going to have you run this as a classification problem with a scikit-learn logistic regression. And this is really great because you can have sort of the reporting of how your model is working. Your model can be trained and giving you an evaluation metric in like 4 or 5 lines of code. And that is what is on this slide right here. So I'm going to have you put this up in just a second, but hopefully now like the last stage, like the pain of the last stage doing that with feature transformation is for the payoff that in scikit-learn it's just a breeze now that we have everything.
This is Sunday afternoon 01. Yeah, okay, so just added a 1 to the end of the first one. Alright, so we'll need to remember that. We might want to like rename it or make a note somehow that it's got cut off in the middle. But yeah, that's alright now.
Is it going to be the final meeting?
Yeah, I guess so. Okay. So what did she say? Do you know? I think we're supposed to do that on the side, is it anyway? Halfway through the session. Decision tree classifier.
Okay, so quick show of hands, how many people have it sort of working and good, keep going? And still working? Okay, so it looks like we have a couple people who are still working, but I'll keep going. Okay, so hopefully that was not quite as painful as the transformations. One of the things that's nice about having something like scikit-learn, where you can have a classifier up and running in just a few lines of code, is it gives you a lot of flexibility to just kind of like swap in new algorithms and explore very quickly to see what might be working the best. Because I'm sure a lot of you have seen this in practice. You might have like a priori an idea about what maybe theoretically could work the best, but usually, speaking for myself, I don't. I just have sort of a standard toolkit of different things I want to try, and then different things will end up working maybe slightly better for different problems. So the ability to experiment is very important in machine learning. So in that spirit, I'm going to have you actually try 2 more classification algorithms now. So it's very similar to what we just did with logistic regression. You don't have to change around the cross-validation or the scoring or anything at all. It's just an issue of importing a new model and declaring that as your new classifier and repeating yourself. So there are 2 different things that I'm going to ask you to do. We'll go back in the next section and talk a little bit more about the theory of these methods, but it's the decision tree classifier and the random forest classifier. So I'm fully aware that I'm asking you to just treat them as black boxes and see what does better, but let me ask you to just treat them as black boxes, fire it up, see what does better. Hopefully it'll be very fast, and then we'll talk about it more in a few minutes.
Okay. So yeah, simply.
There's a typo?
Yeah, like random forest, we're not really wanting to sklearn ensemble, then copy paste sometimes. And then the features and labels of the X and Y.
Maria, she wants us to.
Oh, did I switch them around?
I don't think
No, I
we're
think we are using
training
X
that.
and Y.
Oh,
Do you have
Yeah,
like
like
this?
this.
I don't think we did anything on that. It's like feature labels. That's what she wants us to use. We have something called labels DF.
Yeah, that's
But that's the whole data frame. So I think we might have to make a variable.
so just a
label.
couple quick notes, as one of your colleagues just pointed out to me, very briefly. So first is that random forest classifier is not a tree-based method, it's called an ensemble in sci-kit. So if it's throwing an error in the random forest, that was my fault in the copy-paste here on the slide.
yeah.
And
Features undefined.
the second thing, is that here I call them features and labels, but I think in your notebooks they're called X and Y. So just stick with sort of like the nomenclature of the labels if you're having problems with that. So
here,
for the random
Y.
forest,
Okay.
it's going to be
Capital X,
instead of
lowercase y. Alright.
sklearn.tree, it's going to be sklearn.ensemble. I copied and pasted it.
And then
Okay, good.
okay, just make it a little better. And let's see.
Okay, so show of hands, who's got it working for both the decision tree and the random forest? Okay, great, very good. And still working? Need another minute or two?
Yeah, that's the type.
You, okay.
Should
Would
be.
you like
Oh,
to go over
decision
it
tree
and
should
make
be
it feel-
random forest classifier.
Scalar ensemble.
Okay, so let's keep going. Before I move on, so how many of you at this point you should have looked at 3 different classification algorithms, and you're getting scores for each of them. Show of hands, how many of you are having the best result for the first method we tried, the logistic regression? Good. Okay. How many people got the best results from the decision tree and random forest? Okay, mostly random forest. That was what I was seeing as well. Although decision tree was kind of close in there, so depending on sort of like the random seed that was drawn, that may have been what you got. And we'll talk a lot more about each of these methods sort of in the next section. But I want to just pause and sort of say how much we've accomplished in an hour, right? So we went from sort of nothing, right, to like a working, functional, pretty darn good classifier in the span of an hour. And it wasn't the easiest thing in the world, but it actually wasn't too hard. And this is really important because now that we have this sort of, like I said, quick and dirty thing up and running, everything we do from this point forward is just trying to like tweak knobs and make it a little bit better. So I do want you to sort of consider this a success at this point. And especially since we got started a little bit late, I'm going to try to move a little bit faster through the next section. So maybe not spending quite as much time actually coding, so I can explain some of the concepts in a little bit more detail. And so in the next section, maybe as we keep moving faster, feel free to like make liberal use of the solutions or to refer to this back later. The last thing I'll add before we move on is that this is being recorded and it's going to be posted online. So I know that it's moving really quickly, and so feel free to sort of like go back onto the website later and to use this as a reference in a more leisurely manner. Okay, so deep breath. You're doing really great. Like I said at the beginning, though, we just moved really fast, and we kind of were a little bit sloppy in a couple places in the interest of moving very quickly. So I want to pause and reflect on what we just did and find ways to sort of tighten up a couple of things, a couple places where we were not using totally best practices. So that's going to be sort of this middle portion of the talk. I'll be talking about a slightly better way to be encoding those features. So remember, we turned them from strings into integers. Turns out that has a couple problems with it, and we'll go through that. I'll say a few words about transformers and predictors, which is kind of a technical thing in sci-kit-learn, but will set us up really well for the last part of the talk, where we talk about pipelines and GridSearchCV. And we'll also talk a little bit about the algorithms, because right now I'm just sort of asking you to take it on faith that these are reasonable things, reasonable models to be running. So I feel like I should justify that to you and explain to you a little bit what these algorithms are doing. So with that, let's get started. So think back to when we were reading in the features, right? We had a list of strings that were encoding a bunch of information about all these wells, and we encoded the strings as integers. And we did it in this kind of very quick and dirty way. And one of the problems with that is that strings are not really ordered. I mean, maybe you could say alphabetically ordered, but in general, I think we would agree that like chocolate, vanilla, and strawberry are not ordered strings. Integers are ordered. And so when you put into a machine learning algorithm sort of a quick mapping like we did, it sort of implies that maybe there is an ordering, for example, to the types of well input or the sources of the well water or something like that. And if this is really what you want, especially if you're doing something very careful where you have a lot of domain knowledge and you're like setting up a more explicit mapping, kind of like what we did with the labels, we said that maybe there is an order here that we're trying to reflect. We didn't do that with the features, and so we have something here that's probably not exactly what we want. And this is something that comes a lot. It comes up a lot in machine learning, is that you have this categorical data that's that you have to represent numerically somehow. And how do you sort of deal with that fact that the categories are not ordered, but integers are? And the way that this is usually taken care of is you'll call it dummification, making dummy variables. And the method that's used to do this in scikit-learn is called the one-hot encoder. So let me explain to you just kind of conceptually how the one-hot encoder works. So let's imagine that this is my data. I have a country, which is read in as a string. What we would have done before is we would have said something like United States is 0, Mexico is 1, Canada is 2, and then that has all the problems with it that we just talked about. When you're dummying, what you actually do is you take sort of like these 3 different categories and you expand it out into 3 different columns. So you have a column now for each unique value that you have of that feature. And you're gonna have this sparse matrix now, where you're going to have zeros for all of the sort of categories that it's not for a given row, and then a 1 for whatever category it is. So whatever row number 1 was before, which was United States, now country United States is the column that's been activated, the one category that's hot. This is why it's called a one-hot encoder. And then Mexico and Canada are both zeros, and then likewise for Canada and Mexico as applicable. And so a one-hot encoder is actually supported sort of natively, if you like, in scikit-learn. This is part of the really rich ecosystem that scikit has for feature transformations. And so the way that this works is you're going to have sort of the matrix that has the column that you want to transform, and then it can automatically go in and figure out sort of how many unique integers you have and then map those onto different columns. Again, you do have to have them, I think you do have to have them as integers. So you still have to go through sort of the pain of dealing with that string to integer transformation. But scikit-learn will actually take care of this expansion for you. And so I think I'm going to keep going rather than stop and have you code this up. But hopefully at least now you understand like sort of why you want to do this. And in general, the scikit-learn documentation is fantastic. It's just absolutely a dream, and I think they spend a lot of effort on it, and it shows. So I also don't feel too bad about skipping over this and asking you to go back and do it later, because the documentation is just really good, and in general, it's one of the best resources out there for sort of doing things on your own. So the one-hot encoder in general is how you want to do the dummying of your categorical variables. With that said, let me move on to talk a little bit about transformers and estimators, and then if you like, we can pick this up later. Yeah.
So is there any disadvantage of not having a set with everything 0? Because one hot will be setting hot for 1 to each one, and there's no element on this group that will be all of them zero, all of them variable zero, right?
So a one-hot encoder is basically assuming, yeah, that you have that there's more than one unique value in a given column. So if a column has the same value for like every single row, then yeah, a one-hot encoder will not
No, what
really
I'm saying, for
do
example, let's
anything.
say that you do like in two elements, right? You apply this, or three, right?
Mm-hmm.
You normally, if you do by hand, normally I will do the first value will be everything zero. Second value will be 0 and 1, and the third value will be everything 1. Is there any disadvantage of doing this way versus, so in your case, you'll be like a diagonal matrix. In my case, will be the first one will be everything 0, the second one will be 0, 1, and the third one will be 1, 0.
Oh, so you're thinking of a different way of sort of, instead of having a number of different columns,
Yes,
you
and
now have a
one.
single column, but you're sort of encoding it like in a
Is there
bit wide way.
does
Yeah,
that
so
happen?
I would say that, right, so in this topic, I think in general you do want to do the expansion over many columns because encoding it in sort of a binary way is still implying an ordering to the categories that you probably don't want. Yeah, thank you. Okay, so let's keep going. The next thing that I want to talk about a little bit, we'll pick this up in the last part of the workshop, is transformers and estimators in scikit-learn, and these are slightly technical things. Transformers are things that have the transform method, so at least it's fairly easy to understand, to remember, which one is which. And the idea of a transformer is that something that you put your features into, and it gives you back sort of the features that you started with, but in a different representation and one that might be better for machine learning. So the one-hot encoder is an example for this. You get the same features back that you put in, but now they've been dummied out, and you have this very big sparse matrix that might be better for machine learning for theoretical reasons. Another example of a transformer is principal component analysis to help you get some like latent features, maybe if you work with that. Another thing we'll be doing in the next section or talking about is it's called select k-best. It's basically a feature selection. So it's going to give you back sort of the same features you put in, but it's going to trim away the features that don't seem to be doing as much for you in terms of like helping your model. So these are examples of transformers. An estimator, also a technical term, has the predict method. And so an example of this would be a classification or a regression, basically. That's the way I think of it, as a classification or a regression. So I put in my features, and it gives me back a set of predictions for which class something belongs to, or what the sort of output, the continuous output variable in the case of a regression. So this is your decision tree classifier, your logistic regression, your linear regression, random forest classifier, things like that. In pipelines, we'll come back to this a little bit, but I just wanted to sort of prime that pump, so to speak, by saying a few words about it now, because we've just done both transformers in the form of the one-hot encoder, and also the estimators we did in the last section. So let me spend a few minutes now talking about the different algorithms that I had you use in the last section, because I think that you get the best results when you actually understand what the algorithms are doing under the hood. So let me just spend a few moments talking about the relative strengths and weaknesses. So first was logistic regression. This confused me so much when I first started learning about machine learning, because logistic regression makes it sound like it's a regression algorithm, and it's really like a classification algorithm. So I know that can be a little bit confusing, but it's going to give you sort of the 0, 1, or 2 output. And the way that a logistic works is it uses this logistic function. So f of x is the outcome, the 0, 1, or 2. And then the input variables sort of go into the exponent of this equation here. So, and when you're training, what you're learning is the betas. These are the coefficients on each of your features. So here I have beta 0 and beta 1, and this implies that there's just sort of, the output is just a function of a single variable, x1. But in the case of, in our case, we had many different input features, and so this is actually sort of a much more complicated function that you get in your logistic. And so what happens is that for a given input, you're going to have all of these different betas that are going to be multiplying with your features. That's going to turn this e to the whatever it is into sort of like a 0 or a 1. And then that 0 or the 1 is going to then translate into your f of x being a 0 or a 1 for the class that you're looking at. So that's why it's called a regression, is because it has this kind of like regression looking like term in the exponential, but it really is like a classifier. It's going to give you a label. And this is the sklearn documentation for logistic regression. A logistic regression is an example of a linear model. And I'll talk on the next slide about what that is. But what I wanted to point out in this little thumbnail is that even for something as simple as a logistic regression, scikit-learn gives you a lot of different parameters that you can tune to sort of make this model as tightly coupled to sort of like the exact problem that you're solving as possible. And so when you did your logistic regression in the last section, you just called it with sort of open and close parentheses, which uses a bunch of default arguments. But in general, you're going to want to tune the parameters of your algorithm. You're going to get better output if you are able to go in and like set these parameters to exactly, you know, sort of what fits your problem best. And that's what I'll be talking about in the very last part, pipelines and GridSearchCV, is exactly how do you do that parameter tuning. So with that, let me talk just a little bit about linear models. So logistic regression is nice because it's kind of like the simplest classifier there is. It's very intuitive. You can sort of like work it out by hand what the answer is going to be for any given case. There are a few things that linear models are not particularly good at though, and logistic regression again is an example of a linear model. So here's an example. Let's suppose that I have the functionality of my well and I want to understand how that's related to the age of the well. And so maybe I have something that's very simple, like this first graph that's just linearly sort of like, the functionality is increasing with age, which doesn't make a whole lot of sense, but just bear with me here. Logistic regression is going to do great with this. Likewise, maybe a more intuitive case, the functionality is linearly decreasing with age. Again, logistic regression does super. But what if I have something that's a little bit more complicated, where the shape of my functionality, maybe it's not linear, maybe it is sort of like turning a corner, like it sort of goes up and then has to come back down. This is something that a linear model doesn't deal with particularly well. And so in practice, there are a couple ways to do it. If you really want to use a linear model, you can still use it even if you have features that are sort of shaped like this. What you usually do then is you have to introduce extra terms or extra sort of like features that are things like the log of the age or the age squared. These are some of the standard ones that you add in. Usually it's those two, maybe age cubed. And those can help you capture some of these nonlinearities. But that is, well, it's fine, it works. It can be a little bit painful to have to go through, especially if you have lots of features, and try to understand exactly when you want to be doing this. It also opens you up to overfitting potentially, because you're starting to add in new variables. So you can capture these nonlinearities, but it's sort of like a more manual intervention, and ideally we don't, if possible, want to have to deal with that. So let me walk through a concrete example of like what I mean by an example nonlinear feature, and then we'll talk about the tree-based methods and how they kind of handle this in a more graceful way. So let's suppose that I have some kind of complicated relationship between the age of a well and the functionality. So we'll say that the stuff that's kind of up high in that green region, these are functional wells. The stuff in the middle is the marginal cases, and then if it's near the bottom, then it's not a functional well. So this is just kind of a heuristic to give you an idea. This isn't taken like from the data set exactly. But the scenario here might be something like when you first open up a well, it works really well. No pun intended. This is also tricky when you talk about like functions of different variables, and then you're also talking about functional wells or not. Functions starts to take on many different meanings. And so then maybe there's like some burn-in period, you know, things break, and then as it gets older, those are the really high-quality wells, the one that like are functional no matter what. And so you also have this sort of competing effect at the high age, where those wells are more functional, and you have to like get this kind of weird shape to be represented in your linear model. So a decision tree, which is the second kind of algorithm that we used, in which, at least for me, maybe you have the same experience, you probably did, the decision tree did significantly better than the logistic regression. And so the structure of the decision tree is that it's this kind of binary classification tree, very similar to the other binary trees that you're probably familiar with from sorting integers for an interview or something like that. And so what a decision tree would say with this problem is it's going to take all my training examples and maybe pick off first like the leftmost column. I'm just going to say like, okay, if you're a very young well, age is less than or equal to 1, it looks like, with pretty high purity, you're a functional well. So that first bar is now taken care of. Now we have the 4 bars that are sort of on the right. Let's do another sort of divide and conquer type operation. If you're an old well, these are the wells that have been kind of burned in and they're not breaking anymore. Age is greater than 5, then those are functional as well. Now I'm kind of in this middle region. Those are the ones that I still have left to try to figure out, but I can again sort of go through making orthogonal cuts on the age, and I can sort of get the leaves to each be as pure as possible in one class or the other. That's what a decision tree is doing. So it's able to sort of very gracefully take care of these non-linearities that were giving us trouble with the logistic regression before. A second thing that a decision tree does, and tree-based methods in general do, is they handle the correlations between variables in a fairly elegant way. So let's imagine that now, instead of having this kind of weird relationship between age and functionality, let's say that that's only specific to a certain region. Maybe they used a certain type of construction procedure there, which is prone to giving you this relationship. But if let's say that's true of like wells in the southern part of Africa. But in the northern part of Africa, maybe there's a totally different relationship that I'm seeing, or because of the geography, whatever. There's some kind of relationship between now where a well is built and how it functions in relationship with its age. And so this correlation, again, is something that a linear model isn't going to do super well. In general, if you think that this is true of your data and you really want to use a linear model, you have to introduce what's called an interaction term. So in this case, it would be the region times the age of the well, and then it can handle that. But again, you start to get very large numbers of features that you have to do if you want to like cover all of those correlations, and you're opening yourself up to overfitting. But what a decision tree will do is it'll say something like, first question is, are you in the south? If so, then I'm just going to build that tree that we had on the previous slide, and like everything's cool. If you're not in the south, are you in the north or in the west? And now I'm going to build slightly different trees for each of those 2 cases. And so it can make orthogonal cuts, not just on a single variable at a time, but in multiple variables altogether. And of course, not just 2 variables at a time, but 3 or 4, all of your variables potentially. So it can start to get some of these correlations in a way that a linear model, again, it's just a little bit, it's not optimized for doing that sort of thing. But again, like we had with the linear models, sort of with great power comes great responsibility, and there's a lot of things you have to be careful with when you're using a decision tree. There's some of these parameters, and they have to be tuned. And this is always true of machine learning, right? There's always going to be parameters you have to deal with. So what are the things you have to deal with a decision tree? You have to deal with how it's making the splits, how deep it's allowing the trees to go. Is there a rule about if I have too few examples altogether, do I terminate the tree, or do I allow it to keep branching? And these are all related to basically like how overfit or underfit your tree is going to be. And in general, like if you don't know a priori which model you should use, you definitely don't know like which of these parameter values is probably going to be just right for you. And so what we'll be working toward is GridSearchCV, which is a way of actually searching over as many different parameter values as you want. And it's going to sort of try all the different, it makes this grid of all the parameters that you wanted to try, works through them, and then finds the one that works the best. So GridSearchCV, to sort of like give away the punchline of this talk, GridSearchCV is a really elegant way of sort of doing this parameter tuning, which is kind of painful if you don't have a tool like that. So just quickly, random forest. Most of you probably got this as the best one. That was what I got. Random forest is a tree-based method as well, but it's an ensemble of trees. So what a random forest will do is instead of building a single decision tree, it'll take some randomly sort of allocated piece of the data, so some random number of features and some random number of rows, and it builds a decision tree just for those examples, just for those features. And then it picks another random subset, builds another decision tree. And you can see why this is called a random forest now, because you have many, many trees. And then at the end, all those trees vote. And this is an example of an ensemble because you have sort of this ensemble of models, and it's all of them working together that give you the actual answer that you're going to use. And so random forests, you've probably heard them come up multiple times in the workshop this weekend, and that's because random forests, at least right now, seems to be the best all-purpose algorithm for most problems that we have. So I was being slightly facetious when I said at the beginning, like, you have to try a whole bunch of models, and you have no idea about what's going to work the best. Like random forests usually work the best. And that's not like a theoretically motivated statement. It's because people sit down and they just try everything. And random forest usually kind of bubbles to the top. So when in doubt, if you really only have time for one model, like random forest, do a random forest. A few sort of meta notes on working with random forests. They're awesome. This, like I said, is my favorite algorithm. There are a few things they take care of very nicely. So you can feed in many different kinds of data to them. By that I mean numerical and Boolean. But you don't have to worry about normalizing the features. So sometimes if you have, let's say one of the features is someone's age, which might be between 0 and 100. Another feature might be their income, which is between 0 and 1 million. The fact that 1 million is much larger than 100 can sometimes give you problems with other algorithms. Random forest and tree-based methods in general are robust against this. Like I said, they give you, in general, the best performance, all of the things being equal. They have all the advantages of the tree-based methods in terms of handling the non-linearities in the data and also the correlations. And the thing that makes them better than decision trees is that decision trees can be biased. Random forests can be kind of high variance. You get lots of different answers from all your different trees in your ensemble. But they tend to converge on the correct answer. So even though they're all over the place, they're kind of centered on the right answer. And that's one of the things that gives them their power. Is like you have many different like weak evaluators, but acting together, they give you something that's much stronger. A few things that can be tricky about them. You have all the parameters of a decision tree, plus you're building a bunch of decision trees. So it's like decision tree parameters like squared. The second thing is that they can be a little bit black boxy. Interpretation can be difficult in tree-based methods, and that only gets worse when you have lots and lots of trees to evaluate. And last is that sort of a corollary to that is that you might have, for a given case, if you have 50 trees, you might have 3 or 4 or 5 different answers that your trees are giving you for a given row. And so figuring out how to visualize that and to do some of these important things for like interpreting your model can be a little more difficult with random forest. I think that this pain is sort of worth the gain, but this is not like something that you get for free. You do pay a little bit of a cost relative to something like a logistic regression, which is just super easy, and again, you can sort of like do it with pencil and paper if need be. So that is where we are right now. We have this random forest classifier that you built in the last thing. That seems to give the best score as we were defining it. One thing that you might be wondering is how score is like defined or calculated. Like that's not a very well defined thing. So I want to go back and address that a little bit now. Come up with a slightly more robust way of evaluating the models that we built. We have this sort of elephant in the room of parameter tuning. And we've also, in the process of one-hot encoding the data, we've kind of exploded the feature space. So where before we might have had a column that had 10 different unique values in it, now we have 10 columns. And we've done that over all of our features. And we have something, well, like you'll see in the next slide, that kind of exploded the feature space. And we need to prune that down a little bit more to prevent overfitting. And in general, you might be wondering, we have a lot of open battlefronts right now. And we have the feature selection issue, we have this parameter tuning issue. I think the model is like kind of under control. I think we've converged on random forest, but we still don't like know the best way to be tying this all together. And that's where I'm going with GridSearchCV and with Pipeline, because that will sort of tie all these looses together in kind of like a very nice little package. So let me keep going. We're running a little bit low on time. We have another maybe 15 minutes until nominally the end of this section. So what I'm going to try to do is just push through as quickly as possible, and then I'll stick around for a while. Please feel free to like stay and like code things up and actually get this all working in your IPython notebook. But with that said, let me just power on through to the end. So this is the last portion of the talk. We call it end-to-end workflows with Pipeline and GridSearchCV. I'll deviate from that slightly and first talk about feature selection. But there's a reason that I put this with pipelines and then GridSearchCV, and hopefully that will all become clear in just a moment. Okay, let's talk a little bit about feature selection. Like I said, we have done this thing in one-hot encoding our features, which kind of like exploded the size of the data set. And I know I didn't give you a chance to really put that up, but if I had, here's what you would have found. So first of all, as I was coding this up, I had to actually just drop some features entirely. Because you have something like the name of the village where this well is, and each well is in a different village, or a village might have like 2 or 3 wells or something. So we have 59,000 rows of data, and we might have something like 10,000 different villages that those wells are in. So all of a sudden, this thing that had been 1 column is now like 10,000 columns. And that is not necessarily a situation that you want to be in. So we have to be, I was fairly aggressive in the outset. It actually just sort of getting rid of some of the features. Not because I didn't think they had information, but because they're just like computationally too heavy to be carrying around once we've started dummying them out. So we went from, even after I like sort of aggressively started cutting away some of the worst offenders, in the implementation I had, I went from 39 features in the original sort of version of this to more than 3,000, right? So like over 100-fold increase, which is like, should be a little scary. And if you've never dealt with something like this before, there are a lot of things that are not ideal about carrying around 3,000 features if you don't have to be. So one is that it's computationally heavy. It's going to slow everything down because it has to just look in a lot of different places to try to figure out how to like optimize the model. The second thing is that like, do you really need 3,000 features to capture what's going on? My bet is that mostly no. That probably most of the variation is going to be in just a few dozen or a few hundred features, and the rest of it might give you like marginally more information, but there's probably going to be a core group of features in there that you're going to get most of your performance from. And so being able to identify those and only train your model using those is going to protect you against things like overfitting, which is a real risk right here because we have just so many features. So sci-kit-learn has a transformer. Remember, a transformer is going to take in features and then sort of return to you a new set of features that have been transformed. And the select k-best transformer is actually going to go through in a univariate way, figure out which features are the best ones and just return those back to you. And so you can tell it how many features you want. In this version, I was going to suggest 200. Again, this is not a number that you usually know a priori, and it's something that you have to tune a little bit as you're going through your workflow to see which number is really like kind of in the sweet spot here. The second thing that I set up on our way to like sort of evaluating these models a little bit better. Remember that at the beginning we had this thing called cross-val score. That's how I was asking you to evaluate your models in the first part. And cross-val score does a couple things in one line of code, and that's really nice for moving quickly, but it's not necessarily what you want for your final model. So cross-val score is going to do a couple things. So the first thing is that it's going to split your data into training and testing sets, which of course is always what you want to be doing. But then cross-val score will also take your model, train it on the training data, and then evaluate it and give you back a score that's been calculated on your test data when you pass your test data through the model. And so it doesn't give you a lot of control to say exactly how that training and testing split is happening. It also doesn't give you a lot of control to say exactly what score you want to be seeing. So in terms of just understanding, where am I relatively speaking, it's pretty good, but if you want to really zero in on more specific metrics and understand what's going on, not the best. So what I usually like to use instead of the cross-val score is something that's called classification report. And this will give you sort of a slightly more well-rounded picture of how your classifier is doing. And it gives you more information. This can be a little bit, you have to be careful to not be sort of like overwhelmed by several different things all at once. But let me walk you through sort of what this does, and then in a given situation, there might be one metric or another that you want to optimize for. Sorry. Okay. So classification report is going to basically give you 4 pieces of information for each one of your classes. The first is the precision. That's defined as the true positive rate, so how many people or how many instances you have of this class, and you correctly identify them as being of this class. And then you divide that by the true positive rate plus the false positive rate. So these are the extra things that you erroneously identify as belonging to this class. So in other words, if I'm standing there with a basket of fruit and I say, I think these are oranges, precision will tell you sort of like how many apples you have accidentally in that bag. Recall is sort of the flip side of that. So it's true positive divided by true positive plus false negative. So I'm standing there with my bag of oranges. Recall is going to give me a number that tells me like how many oranges might be sitting in some other bag that says apples on it. F1 score, so in general there's going to be a trade-off between precision and recall. The better you get on one, the other one tends to suffer. F1 score is a nice way of combining those in this sort of like geometric way. so that you're not sort of being pulled in two directions. So when in doubt, I think F1 score is like kind of a nice heuristic for overall model performance. And then last is support. Support is the number of instances you have of a given class. So you can see that in class 1 here, we don't seem to be doing that well. Support gives you maybe a little bit of information why. It looks like there's less than 1,000 instances of class 1. Remember, this is functional, needs repair. Whereas the non-functional or the fully functional wells, we have many more instances of those. It's easier for the classifier to figure out what they look like and then correctly classify new examples of those classes. So this is a little bit of a more comprehensive way of evaluating your model, and I think that it's just a good thing to sort of introduce to you in the spirit of we moved through it very quickly at the beginning, not always making like the best decision, but this is sort of moving more in the direction of the best way of doing your model evaluation. Okay, almost there. So the last major thing I want to talk about is pipelines. So what we were doing before is, or what I was kind of hand waving and you were imagining doing, is you have something like a transformer, like select k-best. You're going to fit this transformer on your training data. You're going to use that sort of, it selects a set of features based on your training data, and then selects also those features in your testing data. This is the sort of transform part of the transformer. So now I have sort of my features selected. I take my training data and I fit my random forest on it, and I use my transform testing data. I pass that into my model, and I get a set of predictions, and that is what I put into my classification report, and everything is really great. This is a little clumsy. Few things are going on. So first thing is that you have, especially, this is a fairly straightforward thing. I'm just doing one transformer and then a classifier, and then I'm done. But if you have a string of transformers, it starts to get a little bit clunky to make sure that you're doing the bookkeeping right in all the stages, that you're actually fitting on your training data and transforming on your testing data. And it sounds very trivial, but the bookkeeping here can be actually, you can screw this up fairly easily. It also means that your code can start to become a little bit more spaghetti-like than you like, because you have to be keeping track of where everything is sort of in this flow. And the last thing is that we want to be able to move very quickly and to try new things based on the various things we know about machine learning. And so it's starting to calcify now, that it's not as easy to sort of swap things in and out. You have to do this very manual intervention, make sure you're training and testing in all the right places. So Pipeline takes care of this in a really lovely way. So what a pipeline does is you have n number, so n is whatever you want it to be, of transformers. So remember, transformers are things that give you back a different version of your features. You can do as many of those chained along sort of in a sequence as you like. And then usually the last thing that you're going to have in that chain of your pipeline is going to be an estimator. So remember, these are your classifiers or your regressor objects. And then, so you tell the pipeline, here are all the steps, do them in this order, and then you just have to call fit on your pipeline. It takes care of sort of all this internal, getting things in the right places, and then you just call predict on your test data. So now we've taken all these different ideas about, I'm going to do the feature selection, I'm going to do the model training, all this stuff, and instead of having to do each one of those individually, you bundle them together into a pipeline, and you just say, pipeline, go do your thing, and it sort of knows how to take care of that. So this is really nice. First of all, it keeps your code really clean. And the second thing is that then, at least for me, it becomes a lot easier to swap in sort of new steps into the pipeline, so you don't have to find the exact line in the code where you need to be doing this step, because sometimes that can get a little bit difficult to do as your code kind of sprawls out and you're trying new things. So pipeline is an object in sci-kit-learn, just like all the other stuff that we've been using. The pipeline code, I will sort of stop and let you come back to this later after we've sort of finished up the thing for today, because I do encourage you to try it. It's conceptually very simple, but it's easy to get it a little bit. The first time or two that you do it, you kind of have to refer to the documentation pretty carefully. But you can see that it's just a few lines. So I have my select k-best thing, that's doing my feature selection. I have my random forest classifier. I have this sort of list of tuples, which are the steps that I want in my pipeline, and then it's just 3 more lines of code after that. So we've gone from whatever this would have been before, 10 or 15 lines of code into 5. So pipelines are really nice sort of for all those sorts of bookkeeping things. Last thing, thing I want to return to is the issue of parameters in your model. So we talked about how we have this random forest this random forest classifier. It has a lot of parameters. Who knows what the correct ones are? A second thing that we've sort of done is introduce the idea of feature selection. And maybe there's some interplay between the number of features that you're using and the parameters that you want to use in your random forest classifier. Because, for example, if you have lots and lots of features, you might have to be more worried about overfitting in your classification step. And the way you would control that overfitting would be tuning the parameters in your random forest. So while one approach to this might be just trying new values, trying different values of, let's say, the number of features that you want to select, maybe anywhere from 10 to all of the features, and you just keep running your model over and over again. You say, like, which one seems to be doing the best. This starts to get really inconvenient when you consider that there could be interplay between not just this feature, or not just this parameter, but potentially all the free parameters in your model. And what you really want to do is make a big grid and do a search over the grid so that if there's any interaction between parameter 1 and parameter 2, you're able to sort of like change them at the same time and find the sweet spot. So certainly like sort of looking through each one of your parameters in a univariate way, so to speak, like that's better than nothing. But in order to like really be comprehensive about it, kind of want to go through them all at the same time. And you find wherever that magic spot is. Obviously not the most comfortable thing to have to do by hand, right? We're talking about like lots of nested loops potentially to search over many different values of parameters. Who knows if the stuff that we try is even going to hit the thing with the best parameter. And this is where GridSearchCV comes in. And then this is where I'll stop talking and I'll allow you to kind of catch up with me. So GridSearchCV is going to take your pipeline and you can give it what's this parameter grid. This is a dictionary. And you can give it the parameters that you want to train, or the parameters that you want to play around with. So in this case, I called it step 1. This might be your like feature selector, 2 underscores, and then the name of the parameter. This is, again, something that you just have to refer to the documentation to get this to work correctly. It can be a little bit clunky the first time around. And then, so let's say that the thing that I'm tuning in this first step of the parameter grid is the number of features that I want to keep. The second thing that I want to tune is the minimum samples of split in my classifier, in my random forest. What GridSearchCV is going to allow you to do is you give it your pipeline and also your parameter grid, and it does this expansion. And you can do it in potentially as many features, as many different parameters as you want, and it'll take care of like this what can be a very like sort of complicated expansion of all the different permutations of these parameters. It'll search through all of them, and it'll find the best one and return it to you. So this is something that's extremely powerful, right? You can do this sort of crosswise search. You're doing everything at the same time. Very compact. You know, I can see exactly what are the parameters that I'm trying. One thing is it's a little slow. So when I was doing this in my IPython notebook, I was finding that it was like significantly slower sometimes than I wanted to put up with. So I will say that to you for those of you who want to stick around and try this afterwards or trying this offline later. You know, sometimes if you're doing like one of these big searches, this is the thing that you set it to go, and you go get a cup of coffee and you come back. And this is not always like a 2-minute operation, but it's so powerful, right? You can just tell it like, here's all the things I want to search through. Like, go find them. And very often you have to like iterate on this a few times. You start to zero in on like the sweet spot of where the perfect combination of parameters is. But this takes care of like that really big sort of expansion of all the different parameters. And you can do it on multiple steps at the same time. That's what I think is particularly cool. So GridSearchCV, you can do just on a single thing by itself. If I just wanted to search a bunch of parameters in my random forest classifier, that's cool. Like, you can do that with GridSearchCV. But you can also do it with the pipeline. You can do it on multiple steps at the same time, which is an incredibly powerful thing. So it takes a little bit of getting used to. And I would encourage you to like sort of try it and struggle with it on your own. But that's the payoff, is that it sort of takes care of this like really painful parameter thing with just, potentially just a few lines of code and a little bit of patience. Okay, so we made it. A few conclusions. Thank you so much for sticking around. And again, hopefully you get a chance to play with this a little bit more offline. But what we've done today, everything we did today was basically in pandas and sci-kit learn. Maybe there was like a little bit of NumPy here and there, but This got us really far, right? It got us not just from the beginning to the end, but to the beginning and the end, and like a fair amount of like sophisticated stuff in the middle. So pandas is going to be great for like the data input and output and doing some of the first order manipulation. Sci-kit, of course, is where all the machine learning lives. The documentation, of course, there's so much more that you can't get through in 2 hours. The documentation on both of these is really fantastic. So I want to encourage you to keep playing with this on your own, not just because it's valuable to know, but because there's really a lot of information out there on the internet. And in general, like that's probably the best resource that you have. But I think you also appreciate now how this is like a fairly simple problem, right? We didn't have to do anything too painful with getting the data or cleaning anything. You know, everything was all set up for us, and it still took us 2 hours. It took us an hour just to get through like sort of the first pass. And in general, this is really fast, right? This is good. But I hope you also now appreciate that things like doing a simple string to integer transform are something that can be non-trivial. Even though it's very easy for us to conceptualize, sometimes getting the code to work can be a little bit less trivial. Hopefully the code that you've written in the first half of the session today will make it so that the next time you see this problem, you just sort of drop in the thing that you've written today and you're ready to go. But also things like defining the problem scope. Is this going to be a classification or a regression problem? Like, seems like it should be simple, but it's worth stopping and thinking about a little bit. And last is that you never truly know if something is going to work until you try it. So having an experimental attitude about this is going to serve you well. And so the last thing that I will leave you with is that there's a constant tension in machine learning and data science between sort of like all the things that you learned today and in your classes and in other tutorials, and the quickest and easiest way to get something written. So we sort of saw that tension today, that we sort of did something quick and easy, and then we stopped and thought about basically every step of that process and said maybe it could be a little bit better. And this reminded me of something I heard when I was in high school, that easy reading is damn hard writing and vice versa. So something that gets you from point A to point B, from the start line to the finish line, as quickly as possible is usually something that you're going to have to go back and iterate on several times. And that vice versa, doing something that is like really rigorously correct the first time is going to take you a while. So in general, what I recommend doing is sort of what we did today, which is get to the end as quickly as possible and then go back and iterate. Waterfall is not your friend in data science because you usually don't know where you're going, and you just need to like try swapping things in and out and have a way of evaluating which one is best. So it's a lot of data science for 2 hours. I really want to thank you so much for your attendance and for your patience. I hope you got something out of this. I would love to stick around for a while and help you out with sort of the stuff in the second half. But if you want to take off, of course I understand. And good luck in all of your data science in the future. I hope to see you around. I know, right?
Couple questions.
Yeah.
The one-hot encoder and pandas get dummies. Is there any difference?
Hypothetically, I don't think there is.
Okay.
And in fact,
just
when
depending
I was,
on what library.
yeah, like what's your favorite? And I'm more of a sci-kit gal who's like learned pandas more recently, so I go with sci-kit, but yeah.
And then the text that goes into the tuples for pipeline.
Yeah.
Does that matter? Or is it just for your own metadata?
Yeah, so I think